Okay, thanks everyone for coming. My pleasure to introduce Mikel Diez. That's that right. Has come here from the University of Bristol and is going to talk to us about melt right from the pause to the eruption. Go for it.
Hi everyone. So I'm Mikel Diez from based at Bristol University, and well, first of all, I'm delighted to be here at the new program and having the opportunity to interact with mathematicians and other earth scientists to tackle common problems. My background, I have to say, is in geology originally. Then I moved into physical volcanology for a PhD, and you can see here I was working in the Villarrica volcano a few years ago, and also Socorro Island in Mexican Pacific, doing some field work at the top. And oh, by the way, this is Andrew Woods. I believe he's a mathematician here, and I managed to meet him, and he's got some transport problems with him and all. And so yeah, I've always been attracted by the idea of working with mathematicians, but I have to admit that most of the time the interaction has resulted in a steep learning course, but here I am. I have to say I've enjoyed learning from them, and yeah, it's been, I think, pretty rewarding overall. So I'm kind of a bit off. I mean, I know that the program is titled Melt in the Mantle, but I'll bring Melt in the Crust because I believe there's common themes between both, and in a way, what happens in the crust in terms of magmatism depends sometimes, not always, though, depends on what happens from melts, mafic melts coming from the mantle. As I said, it's not always the case. For example, in orogenesis, mountain building, when you have thickening, and you have progress heating, lower crust might melt, and sometimes there's no contribution from the mantle at all, as geochemistry shows, for example, in Himalayas, to just say some examples. But I'll be touching on problems like that. But mainly we can have in mind problems, magmatic systems in Earth, for example, something like that. So the title is just sounds a bit ambitious, but it's just my reflection on trying to make progress little by little by building a hypothesis from the bottom up, from the brain all the way. It's just expressing my desire more than because I'm stuck at the micro scale still. What else? Well, the talk I organized just says that I give a brief overview of how I view the magmatic system, very idealized, and then walk you through the different time scales and spatial scales, from core all the way to eruption, plutons and eruptions. Then touch a little bit of tectonomagmatic interaction briefly, and then move into microscale two-phase theory and some work I did with Andrew Hogg in the mathematics department, deriving some performing some linear stability analysis on two-phase flows to understand small scale shear bands and things like that. And then finally give you a glimpse on a project called Pluton's Project that is about imaging an active magmatic system in the Andean crust, in which I am involved. And I think it's a good opportunity to bring all these ideas together about mechanisms and the crossing of a scale upwards and so on and so forth, just to end with a couple of slides on the work I'd like to tackle while here in Cambridge for a few weeks. So let me show you a very idealized cartoon of what a magmatic system can be. This is perhaps a section in the lithosphere. We have Moho here, and ponding basalts are right there, differentiating and interacting with the lower crust to generate magmas that are going to focus and be transported outwards and placed in the mid-crust to form plutons and magmatic reservoirs that eventually will erupt in eruptions. Talking to geologists, of course, they keep saying me that magmatic systems are I think that they use this word sort of idiosyncratic, but I still think there's patterns, and that we can understand that almost any magmatic system would share. So that's what this graph is intending to grasp, some sort of idealized picture of it. So if we go into the solar system, let me show you what I learned from it during my last years in my career. I started from volcanism at the surface. This is Calbuco, by the way, from last year. It was a VI 3 or 4. I missed it for 3 weeks. I was doing fieldwork there with my Chilean friends, and I witnessed the Arica eruption that missed Calbuco, that went off like 3 weeks after leaving Chile. So at the beginning, I did some work years back on conduit flow mechanics and eruption column physics, but it was clear to me that in order to understand what happens at the surface, I had to get down and have an idea of how the architecture of the system is organized in terms of transport structures and reservoirs. And these are some examples of later research I carried out in Utah. These are examples of magmatic conduits, plugs, seals, and well, this is dikes, sorry, and seals. And I was doing research to understand how the eruption initiates from these reservoirs, focused through the transport mechanisms all the way to the surface, and not only mapping them and looking at field relations, but also doing some geophysics to uncover the roots. So that's how I built my understanding for the solar system, pretty much. Then I got involved, as I said, in the Andean project, and using subsurface geophysics, we could get insights into the internal structure of the system at deeper levels. But of course, here we lose more touch with reality and with outcrop, and you have to rely more on indirect techniques to measure the architecture of the system. So the problem becomes more inverse and non-unique and definitely tougher. So now let me just give some examples of this process of scales from basically melting the pores, where melting occurs at grain boundaries, and the pores then segregates into shear bands, as I observed in fieldwork that I did in Utah. This is a tilted climbing section of a seal, a reservoir climbing up section towards the surface at 3 kilometers depth, and within I observed this shear, what I interpret as segregations of melt. But these are not the only examples, of course. Magmatics, for example, in the crust are just packed with these leucosomes, or structures that tell structural geologists something about how melt flow through them and how segregated from the pores into these veins at the centimeter scale. These magmatics are very complex rocks. They are polygenetic. They record not only the melting of the crust, but also the segregation, accumulation, and transport of melt. And they separate the upper crust where the plutons and the granites are placed out of them from the restitic lower crust residue. So they are very, very complex but interesting rocks that give us clues of how, in reality, in the field, we scale from pores and grain boundaries into slightly larger melt bands. In terms of time scales, the prograde heating melting definitely takes a very long time. So, for example, larger than 1 million years is normally accepted, but I've seen evidence from geochronologists in Taupo in New Zealand claiming very, very fast melting rates in beyond a few years. And they claim that the whole protolith is pretty much molten in that time scale, which it's kind of shocking. For segregation into shear bands, geochronological studies and theoretical studies gives a wide range between 10 to 4 years, perhaps. Now, in going from, we go from this centimeter scale shear bands into larger scales, such as transport structures. So the dikes, these are basaltic dikes again, in the shallow crust, Utah, of 1 to 2 meters thick, These are some plaques. Sometimes these dikes merge into plaques, or these plaques emerge from the seals. But they are never larger than a few tens of meters in diameter. So those are the scales, from the centimeter to tens of meters in diameter. And these are examples from silicic volcanism. This is mafic, basaltic transport structures. These would be dikes within a magmatic terrain in Antarctica by structural geologist Brown. Again, this is the scale. This is a person, and these things would be, again, a few meters thick. So with silicic magmas, dikes tend to be thicker. As we can see here, this is another example from Pangong Range, Karakoram, I think, in northwest India. And this is, again, the geologist for scale. You can see the thickness. This is a conjugate set of dikes, a calcosilicate host rock, and they, again, a few meters scale. Time scales are well constrained for transport to dikes. There's been quite a bit of theoretical work, as you probably know, by Lister, Rubin, Bedford, for example, and they are definitely faster than a year for magma transport. Now we go another step upwards from the dikes into plutons, and it's a very quite remarkable exposure in Chile, central Chile. It's called Gloria Pluton. Colleagues from there, Santiago, have mapped the Pluton and constrained the flow within it upon placement and so on. But the point is that here we're going to scales that range from, say, 1 to tens of kilometers, and volumes that range from 100 cubic kilometers to all the way up to 1,000 cubic kilometers. Now, the time for building these things out of dikes is constrained to be from months, again, very wide range, from months to more than 1 million years, depending on the size of the Pluton and the input of magma infrared. Very interesting is the relationship between Plutons and calderas and ignimbrite eruptions at the surface. This is currently under debate. I don't think there's much discussion on whether they are timely related. It's more on whether they are related in space. Some workers said that whenever you have Plutons, you don't have eruptions, caldera eruptions, or ignimbrite eruptions, and vice versa. But let's not get into the details of that. I'm just showing you here Crater Lake that erupted 6,000 years before Christ. With a VI, this is volcanic explosivity index of 6. Let me just stop and explain a bit about this, because that's for us, for volcanologists, it's sort of like the Richter scale. It's a small. It gives a sense of the magnitude of the eruption, and it incorporates the volume erupted in the eruption, the material erupted, and the eruption, the height of the eruption column, basically. So to feed intuition, I put these volumes here so you can make the link with Plutons and potential magmatic reservoirs from which eruptions take place. An example of VI3 is something like this. This is Tungurahua from a couple of years ago. This is no more than 10 kilometers high, VI3 eruption, and a very tiny intrusion, really. I mean, this is probably a small seal, maybe the ones you've seen, slightly larger. Then we have Mons St. Helens, a bit bigger, but still in terms of the erupted volume, when you compare with plutonic volumes, it's still very small. We are talking about 1 cubic kilometer, nothing very impressive. Now, then, when we get into 6 and higher, we were talking already about eruptions like Crater Lake that you saw. So these are big things, and the reservoirs of these things probably look like the Plutons you've seen in Chile. These are 100 cubic kilometers and above. They are already big, and they fit this sort of eruptions. Tambora would be another example of this sort of eruption, quite famous physical volcanology. And in the higher end, we have what volcanologists call super eruptions. And a typical example is Yellowstone, with eruptions of 1,000 cubic kilometers and above. These are already very large Plutons. And another spectacular example, perhaps, is Taupo, Mount Taupo in New Zealand. You can see the lake here is pretty large, This a photo by volcanic Stephen Self, and you can have a sense of the immensity of the volumes and extensions we are talking about, and of the ejection, the size of these eruptions. Same feeling when if you've been to Yellowstone. I mean, if you put yourself in the middle of a lake, you can have an idea how big these eruptions can be, and of course the reservoirs from which they erupted, perhaps the pollutants that are below. And just add this, because this is a constraint from geochronology again. This is a Senna-Christ of zircon, and geochronologists use them to date magmatic events. And in a way, they back to what I said before, these scientists constrain the wholesale melting, the complete melting of the protolith to fit this eruption in less than 10 years. This is for me hard to visualize, but I don't know, I'm not a geochronologist or anything. This is the sort of timescales they are bringing on the table. Obviously, I think they claim open system melting, maybe flux, fluid present melting, but very interesting, very surprisingly fast timescales for these super eruptions. So in short, going from the volumes that are cubic millimeter or less through shear bands into dikes, pollutants, and eruptions, we find timescales that range widely. Spatially, we go from, as I said, from cubic millimeter or less, all the way to 1,000 kilometers or more. And in terms of timescales, again, this is pretty wide. The range is very wide from months, which is the timescales that we find in eruptions, all the way to million years or longer for pollutant emplacement, pollutant growth, and so on. So some outstanding questions are there. In volcanology, I noticed in my early years that, for example, the chamber, the magma chamber, and the dike are always there. They rarely put there and do the calculations, but it's rarely explained how you get there, how you nucleate the dike, how you grow the chamber, how you go from the pore into a large volume reservoir. These are hard questions. And again, it kind of surprises me. I mean, it blows my mind how to generate 1 cubic kilometers of melt, get that volume ready for large eruptions in Bristol salocrust in timescales that geochronologists are sort of constraining. So, very interesting, hard questions. In terms of extraction and ascent mechanisms, there was a big controversy in the 90s. Basically, some group of scientists defending diking as the leading transport mechanism, magma through the crust, and others defending diappear or en masse ascent, that is, channel versus en masse, basically. And of course, questions like what would control the transition between diking and diaphorism would demand models that incorporate melting rate and segregation mechanisms at source, so we can understand how do we switch from one to another. But again, this was a matter in the 90s, matter of debate. This links also with another outstanding question, the question of focusing the magma flow out of a large volume of dispersed, very small pores and grain boundaries. What are the mechanisms behind this? Is Rayleigh-Taylor convective instability? Is tectonomagmatic interaction playing a role? Again, what I believe is sure is that we definitely need to understand the mechanisms that operate at that scale in the protoliths, at the same time undergoing phase transition and possibly deformation to build reliable and realistic hypotheses based on sound physical principles. So now, speaking of information, I want to show you some examples of tectonomagmatic interaction. But when I was involved in them, I was more thinking macro scale, nothing micro, and definitely not dealing with two-phase physics and the scalings I've shown. So this is an example in Nicaragua, right here, where cocos plate subducts below the Caribbean, generating this volcanic arc here. I studied Cerro Negro volcano, And it was a very interesting eruption because right after 3 magnitude 5 earthquakes strikes the lateral earthquakes, the volcano erupted. It took about, from the main shocks, about 11-12 hours. The volcano ruptured through the south flank, not through the central bend, and fitted this Strombolian-like activity through a 200-meter long fracture. So I studied it from the point of view using a stress analysis, static stress changes, and so on, also to explain the distribution of aftershocks, trying to put things together, not in much detail, but to build a hypothesis to explain what happened. And the way I saw it basically was that the shocks changed the stress, the static stress, dilated the system at the source perhaps, and prompted the ascent of magma through the crust all the way to the surface through this fissure. More recently, seismic tomography revealed in this area a very shallow anomaly, possibly indicating that the soils go to the surface. But again, I'm aware that these problems with tectonomagmatic or volcano-tectonic interaction are very tough. It's like the chicken and the egg. What was first? It was first tectonics and then eruption, or vice versa, and so on. So I don't know. It was just my explanation. But in any case, what is sure is that tectonics and magmatism interact at different scales. Same in Chile. Another place I'm a bit familiar with. These guys, structural geologists there in the Altiplano, where Nazca sits below South America, and the crust is thickened. The Altiplano, they report a set of northwest-southeast faults and claim that they interact with the reservoirs beneath crust, possibly pumping melts from different depths. Perhaps more compelling is the south volcanic zone. This is central, as I said, in the Altiplano. My Chilean colleagues here told me that the evidence for volcano-tectonic interaction is even more spectacular, and they claim that you have even lithospheric sutures there, pumping melt from the lower crust all the way to the surface. And one of the most spectacular examples, they say, in terms of patterns, is conjugate sets of lineaments pumping the northwest silicic and the northeast mafic at the same time. So there's definitely lots of geological patterns for these interactions between tectonics and magmatism. So at that point, when I was working on tectonomagmatics and volcanic tectonics, I was looking and I wasn't aware of the microscale and the physics of the microscale. I mean, I look at outcrops, my own and other people's outcrops, and somehow I knew that at smaller scale there were these shear bands and land segregations, but didn't know how they formed. So I came into two-phase literature and started digesting a bit of the physics and the mechanisms behind, and I learned how with two-phase mixtures with a weaker phase, when you deform them, you sort of coagulate or aggregate the weaker phase and form these bands that eventually can localize strain. And also, I came across damage mechanics, which I find really interesting, particularly looking at rocks. I know rocks get damaged, and they develop defects, cracks, and all these sort of structures. So, all in all, I came to understand the mechanism for the instability of deformation through this loop, basically, where when you have a damaged region in your rock, you attract melting to it that leads to weakening, further focusing on strain localization that leads again to more damage and so on, more meltdown and weakening through this loop until you get your deformation going and your bands form. So at that time, the learning curve was very steep, I have to admit, and I knocked on Andrew's door. He's a mathematician at Bristol, very kind, and we've been intermittently meeting and trying to tackle this problem from a mathematical point of view. Well, as you know better than me, I've shown you that at least in reality, rocks, particularly in the crust, definitely have evidence for these segregations and these melt bands and processes. There's been a bunch of, in the last 20 years, theoretical studies in trying to explain these shear bands. Again, you know much better than me all the literature, and also experiments on molten aggregates that I think convincingly show that melt organizing into shallow bands when shear. So to me, what I gathered and understood is that these two-phase mixtures are unstable. Their deformation is unstable to a couple mechanisms. Basically, this one, you know, is just a mechanical porosity weakening effect here. So if we maintain the stress constant in our sample and introduce variation in porosity, affecting porosity decreases, and then fluid pressure in a region of increased porosity is going to decrease as well, and there you go. There you have your instability. So fluid accumulates where it was already concentrated. That's how you came to understand it. And this was the pioneering work of Stevenson in the '89. Surface tension, I gathered from work like here by Junder, 2006. Now have both effects. Can be redistributing or stabilizing, though the hydro angles beneath the disaggregation fraction, which is common for porcelain molten rocks in the crust, or it can be self-separating or stabilizing and hydrate the hydro angles, like 60 or at above disaggregation fraction. This is an interesting case, for example, for ultramafic melts in the mantle. Some workers like Rabinovich and Ricard have proposed that down there maybe this destabilizing effect might be nucleating seals and dikes for ascent to sour levels. So I employed two-phase damage, continuum damage two-phase theory by Bercovici and Ricard, which might be familiar with it. It's a mixture theory that averages quantities over volume. Main assumptions are that both matrix and fluid flow are incompressible and Newtonian. They have constant viscosities. The mixture remains isotropic carbon deformation, and I'm going to assume that below the disaggregation fractions, partial molten rocks more than suspensions. So the governing equations, mass conservation, well known, momentum, so both the fluid and the matrix fields are subject to different pressures. Here, in this term, we have the pressure jump between both pressure fields. Here's the gradients. He accounts for gradients in surface tension, and then they introduce this omega parameter that basically controls the partitioning of surface energy across the interface, and yeah, it sort of captures the embedding of one phase with respect to the other, which is carrying the effect of the interface, in other words. So this is perhaps the key of the theory. It's the damage equation. It's an energy conservation statement, work statement. It relates the work done by the pressure fields and also by the viscous deformation, the diatoric stresses acting on the mixture, and the work done at the interface by the surface tension. So basically, if I understood correctly, these forces, the pressure field and the diatoric stresses, act at the interface against surface tension, storing surface energy, and that's controlled by this term here that controls the partitioning into a reversible part and an irreversible friction heat-like part. So the part that is stored as surface energy is controlled by F, and it has this shape, and this is an important parameter here. Controls the variability of the deformational work partitioning as a function of dilation rate, and that's how it controls also the generation of cracks in the surface area. So Andrew Hogg performed linear stability on these equations, introducing multidimensional linear background flows. So he introduced the basic state and the the background flow is linear. You can see it here is mediated through this tensor, must be trace-free, and it contains the kinematics of the background flow we are going to impose. He introduced a special type of normal modes. They call them fluid dynamic scaling modes. So these normal modes have time-dependent growth rates and time-dependent wave vectors. And he came to solutions of this form. So after assuming that the matrix viscosity is larger than the fluid viscosity, which is reasonable, at least the crust, and also assuming that the partitioning coefficient, that is the surface partitioning coefficient is 0, so most of the interfacial effects are carried by the matrix. He came to these solutions, a differential equation for the time evolution of the wave vector, and then an instantaneous growth rate that depends on the numerator here on capillary number, capillary effects. Even here, after adimensionalization, it's just a relation between surface tension forces and viscous stresses. Surface tension and viscous stresses. Then we have this term here that controls tectonic deformation, viscous deformation. And down here, B, is this term that contains surface generation, the work stored, the new surface area created, damage term, if you like, that clearly accelerates the porosity instability. Down here, C is dependent on the compaction length, and he derives a condition here such that tell us perturbations growing the fastest are the smallest within the continuum limit. Yeah, well, these are too small, we can assume C equals 0 and so on. So,
can I just stop you at that point? Andy,
yeah.
what are you assuming about how the shear viscosity depends on porosity in this?
Well, shear is viscosity is constant. Oh, permeability
is constant shear viscosity.
It's constant. It's not rate dependent, the viscosity.
There's no porosity weakening in the shear viscosity.
Let's get back to it later. And
It governs the whole effect.
That's the whole effect. Yeah, I just wondered whether, because normally, yes, when you're doing this instability, you say that the shear viscosity depends on some exponential e to the minus alpha phi or something like that. There's some alpha which controls how much the porosity weakens the effective shear viscosity. I don't see where that alpha comes into this, so I don't know. I assume
If you don't weaken, you don't get any instability.
so. There is some weakening, but it's not the usual. Have you got an effective shear viscosity just going 1 minus phi times some constant? Because that would be big, but yeah, if you do
That was in the old Berkovici model.
yeah, that's in the old Berkovici. That's what I'm thinking this is
Yeah.
coming from. Yeah, so in the old Berkovici thing, you say the matrix has a constant viscosity mu m, then the effective shear viscosity of the two-phase aggregate is 1 minus phi mu m. So there is a weakening, but it's not slight compared to what one normally thinks of as I don't know, a factor of e to the minus 25 phi or something like that.
Okay.
Sorry, it's just
No, that's
well,
fine.
we could go through this as a point.
Yeah, let's get back to
Okay,
it
so-
later, and you clarify to me this details. Okay, so in simple shear, at early times, Andy derived this solution. We have a sketch here for three-dimensional shear with a wave vector here in the decomposition of the wave vector in the three components and the angles there. And he said that it maximized when alpha sub 0 is equal to pi divided by 2, and beta 0, which is the angle between the wave vector and the y-axis, this is a typo actually, is pi divided by 4. And this is the stress field solution of 45 degrees that also found in other models. But furthermore, when damage is present or is prominent, it's higher shear rates, the denominator can become negative if this condition is satisfied. So for beta 3/4 times pi, that's this angle 135, we can have a maximum growth oriented like that. So I would call that the damage solution that undefined. So in pure shear, so stagnation point flow, again, very times, we find that the growth rate of the instability stress is fast, and another, again, kinematics of flow goes like that. So we have a K wave vector oriented like this, and the angle with the vertical, with the z-axis given by theta. So again, the growth rate maximizes with theta p divided by 2, which is again a well-known solution from Stevenson, for example, not workers. It's a stress field solution where you have maximum growth subparallel to maximum compression. So again, damage solution. When denominator becomes negative, shear rates are high, you have damage. The orientations that maximize growth rate are these ones, horizontal high angles with maximum compression. Then he carried on and combined both and defined transpression and transtension. These are interesting for structural geologists in the field, and so he did some analysis, and we can see that the growth rate here is slightly faster. No big deal. And the orientations are just a combination of all the previous simple and pure shear solutions. So if we look now at the time evolution of the perturbations, we had 3 wave vectors there. What is interesting perhaps is that the wavelengths, the wave vectors of the velocity perturbations changes through time. And to illustrate that, I built these plots in which I represent here shearing region with some perturbation, dimensionless perturbation. And here we have a graph showing the evolution of the perturbations, the initial angle at the base and time with the vertical. So the contour solutions are solutions that govern rotation of the perturbations, and the surface plot is just the instantaneous growth rate. So we can see, for example, we start 45 degrees very fast, and then the growth rates start decaying until perturbations become vertical, get into the compression regime and expel fluid out of them and start decaying. So you can see the effect of the wavelength increase upon shearing here as time evolves. So in summary, the background shear flow rotates porosity perturbations. Their wavelength changes through time, so changes linearly with time in simple shear and exponentially in pure shear. So in pure shear, the growth rates are twice faster than simple shear, and both in transpression and transtension are slightly faster than simple and pure shear. And we found this high angle solution, damage solution with respect to maximum compression that seems to dominate when at high rates, high shear rates. So as geologists or interested in applications to geology, I was thinking about simple shear systems. So I looked at Himalaya and some examples by Richard and Weinberg that is one of the most remarkable, because they claim you can work from source to Pluton to battery all the way without losing continuity. And again, in this picture, you can see what you can find there. There are like shear zones, melt bands, dike networks, and so on. So I was interested in applying the linear solutions to see how fast these instabilities grow in a setting like this. And after a few refolding times, 10 to the 4 years, you can develop without damage these impregnations, which is reasonable with geochronal impact constraints. And if you have damage, and you shear them fast to shear zones a few meters across, you can have higher growth rates, shorter growth times in the order of 1,000 years or so. So it's not crazy. Another interesting, perhaps Eureka application is in pure shear. It's for the nucleation of dikes, as I said. So in going from core into transport structures, one of the questions I have is, so how do you nucleate these dikes? Instead of assuming they're there, I'm interested in how do you get there. And these sort of theoretical models and approach can give us some insights into the earliest stages of nucleation. So for example, I think it might be interesting to see that in pure shear, so let's say for example in a stretching piece of lithosphere or in a thickening crust, if you're loading, you put the protolith in a state of pure shear and stagnation flow, and the instabilities will grow exponentially in time. This is very preliminary. I wonder if you can get the right scales through these mechanisms. An alternative would be just a percolation approach in which you have a bunch of these channels that eventually sort of cluster, and it would be interesting to see when you get the right conditions for dike propagation, such that the stress of the tip matches the strength of the rock, and you can start bringing the magma upwards by brittle fracture. I was playing here years ago with some models to understand if you have a homogeneous, this is an phase, unstable magma layer, trying to understand what the strain rates are. So this is it's just the invariant, the second invariant of the strain rate to see what would happen on top and what were the areas where the shear rates are highest, and perhaps suggest that dikes could nucleate there. More interesting to me is when Weinberg, he's an Australian structural geologist, came to me in an IDU and brought to my attention this discrepancy. For him, these were sort of interesting examples of how the field doesn't agree with theory and experiments, and he was saying that pretty much what he finds in many places, in magmatism terrains mostly, is the high angle orientation. So I was back then interested in this, and then realized that maybe it's a suggestion that a mechanism like damage mechanism could be operating and help us also explain these sort of structures. Same in pure shear, he found places that were put in loading. So you can see here the pre-existing foliation or layering folded. And these are the segregations that form kinematically. And again, they seem to form at a high angle from sigma 1. This is an example from Lakeside Pluton, Pilgar and Crater in Western Australia, approximately molten tonalite, and maybe suggestive again, damage like planar wall formation of these sort of rocks. I look into experiments, and there's a lot of work done, but Parsons et al. Captured my attention because on top of producing the shallow bands in the aggregate, he found that after 100 hours of annealing, there were surface tension would redistribute the melt. So I thought that this could be interesting to look at from a theoretical perspective using the solutions that Andy derived, and use the parameters there and try to see how the solutions would predict orientations in this situation. And I ran a case without damage, another case with damage. So the case with no damage, we can see in the plots I've shown before that the perturbations grow the fastest all the time at 45 degrees. However, when we take into account damage, we can see that the perturbations start growing at shallower angles over time, And I found this interesting. I thought, well, maybe there's a contribution again from generation of new surface and damage mechanism to explaining the shallowness of this band. So as shearing progresses, damage is stored in a direction which is parallel to the maximum elongation. It's sort of competing with the stress field solution. So through time, it's sort of favoring an intermediate solution, bringing the bands shallower. But again, I mean, it's just a suggestion. It could be a mechanism that operates along with the other ones proposed, such as shear dependent discussed. So of course, there's many limitations and other questions, and I'm aware of some. This is a linear stability analysis, so it's only valid for early stages. Also, magmatites, where we find these field examples. These are complex rocks, as I said. They melt, they segregate, they transport the melt, they accumulate the melt. Many factors included. So we haven't taken into account, for example, temperature variations and phase transitions. But I'm aware that Schrabeck and Raj have made progress on those lines, combining compaction and phase transition. Also, I haven't taken into account specific recrystallization mechanisms. I'm aware Berkovich has developed new theories, but I wanted to start from the simplest and see how it goes. So not accounted for explicitly. Now, of course, a major challenge still is the upscaling and the crossing of scales from centimeter or millimeter pores, veins, to meter and kilometer size structures. And perhaps the growing wavelengths might shed light on this, at least help to me climbing from the millimeter into the centimeter or meter scales, because recall that in pure shear they seem to grow exponentially. But there's still a lot of work to do. So just before I finish, from here on I'll give you a very brief overview of what this project is about. It's called Plutons, and it's about imaging a subsurface active magmatic system in the Andes. So I think it's a very good opportunity to bring all these mechanisms and the crossing of the scales into building hypotheses of how these systems might work. I'll give you just a few observations from geology and seismology, but if any one of you is interested in more detail, Matt Pritchard is the leading scientist on this. It's going to come, I think, June the 8th or something like that, to give a more detailed talk from the observational point of view and all the findings in this region of the world. And then as I said, I'll finish by just giving you some ideas of the sort of work I would like to carry out here, while here in Cambridge. So this project is carried out in the Altiplano Puna, Bolivian Andes. Here is Central Andes. Remember that before I showed you tectonomagmatic samples of this area and surroundings of the southern zone, which is around here. This is very interesting from the volcanological point of view and the plutonic point of view. And in fact, one of the objectives of the project was to explore the connection between the plutons and the Ignimbrite caldera eruptions, see if by subsurface imaging and geology they could find out how these are connected in a system that is active. So this area is pretty much packed with calderas. This is one of the largest regions, neogen regions, with the largest eruptions in the world. These eruptions are all VEI 8 and above. This region has hosted more than 9 super eruptions of this size. So this is, you don't see much in the geology. It's covered by Ignimbrites everywhere, which is the product of the eruptions. And there's also dome complex systems and fusive volcanoes interdispersed between the calderas at the surface. Very, very interesting from the volcanological point of view. One of the questions, this is a plot of the cumulative ejected volume. We can see it's pulsated, so you have heights through the last 10 million years. And for the last 2 million years, it seems that the activity there has waned, but we cannot rule out that the system is still active and something's going on, especially from deformation, because what triggered the project was an enormous deformation signal in the radar, in the INSAR, multiplied pre-chart, and this is about almost 300 kilometers across, and it has a very interesting pattern. It has a sombrero, they call it some Mexican sombrero-like pattern, where you have central uplift at about 1 centimeter per year, and then you have a moat surrounding it that's actually subsiding at a similar rate. To my knowledge, I think they believe this is just the short-term response of the magmatic system, the shallow part of the magmatic system, nothing big. But there's still research going on in this regard. In fact, most of the research is actually focused on the shallowest part of the system. So, subsurface images. So looking below, we've been interacting with seismologists, and they've carried out seismic tomography. This is done by Ward, and he has mapped this velocity anomaly at a depth of about 15 kilometers. It's about 11 kilometers thick and 200 kilometers in diameter, and they believe it's partially molten. But of course, the melt fractions and all, it's been debated. Some of them have suggested very high melt fractions, even above the disaggregation level, which is perhaps too much. And others have actually constrained lower melt fractions in the order of 10% or less. Also, another team has carried out magnetotelluric measurements, and again, we can see a conductor here at about the same depth. They cannot see the structure below, but there's something conductive there that coincides with the surface, the seismics. There's also these channels of high conductivity, but it's unclear whether there's a melt or a gas. They are not sure about it, but there's definitely structures connecting the shallow magmatic system with surface. Also, I was involved in the gravity inversion analysis, and of course, melts and fluids in the reservoir create anomalies. And my colleague here, the author, was running these inversions to see if we could see some of these structures, these gravity anomalies, and very non-unique. This is for different contrast in density, and you have variation from very dispersed structures down here to very continuous structures to something that could resemble the fingers that you could see in the resistivity. But as I said, it's quite non-unique and diverse. At this point, it's hard to say. Mike West from Alaska carried out more tomography, shear wave tomography, and in addition to the magmatic body at 15 kilometers, he is pretty confident that there's an anomaly. It is quite with a high aspect ratio. The cube is sort of tabular. There's some smearing here, so it's probably narrower than it looks. And this observation, along with the geology and the petrology of the area and all, prompt me to start thinking about hypothesis for the whole system, not only for the shallow part. So conceptually, I divided the system in 3 parts. Lower system at the Moho, where we know the basalt is being ponded there. Mid-system, where the magma from the lower is transported and placed into plutons, and then a shallow system from which is fed from magmas from the mid-system, which would be the APMB, into the reservoirs that they feed the volcanic eruptions. And of course, my intention is to bring the understanding from the field and from the theoretical analysis from the bottom up to trying to cross the scales in a geological, physical, meaningful way, such that, for example, basalt here differentiates into andesite, and then this magma hits the host of the lower system, partially melting it, and upon deformation, we could just segregate into bands that somehow cross scales up to dikes that transport metal to the surface, to shallower levels, feeding plutons, that eventually grow into batholiths and so on. Same problem here. Somehow the magma has to focus into this region to allow transport into shallower system that will feed eruption. Same sort of thinking, from pore to largest structures and even forming lithosphere. So more in detail, right at the moho where the basalt ponds, you could have pre-existing lithospheric suture, as the Chileans suggest, or maybe by the damage mechanisms I mentioned, you could nucleate it, partially melt, the region is shearing, so you have the feedback between damage and weakening, focusing, working. So you could nucleate shear zones and probably melt through it, through channels, dikes, kind of like in a zippering effect upwards until it's in place at some rheological contrast, mechanical contrast in the mid-crust, forming a pluton like the ones I've shown before. That could be repeated in time. So for example, this process could sort of follow faulting or jumping of shear zones from place to place. This is a cartoon from geologists, there's no physics here, but they draw these structures that I think they meant to be dikes, but no one is really sure. But if you repeat the mechanisms I posed before, through time and space, you could end up building plutons and batholiths in the mid-crust as we observe. I mentioned batholiths because what we are dealing with here in the Andes is very, very large. I mean, it's the product of an amalgamation of many plutons. And if we look at the empirical evidence of these intrusives from geology, the Altiplano Puna body image with geophysics definitely plots in something that resembles an incipient batholith. So somehow it reflects the early stages of development of these crystal bodies. So standing questions again, as before, I mean, we inherit from before that what are the focusing mechanisms at the lower and middle levels? Is it the shear zone development, damage operating and focusing deformation and ascent, or maybe it is Rayleigh-Taylor convective overturning? What are the mechanisms to cross the spatial scales, that is going from segregation to transport and to emplacement and eruption? So reasoning by analogy from exposed geology, I think, will help this point. And also very interesting is the question, when you have peak magmatic activity, is the question of whether the lower and the mid systems interact to produce andesites, dacites, and ignimbrites in time and space, as this graph, empirical graph, shows here, with pulses of increased magmatic activity in the last 10 million years. So, just to finish, I like to tackle these sort of problems here at the fundamental level to start with. So, for example, in the mid and shallow system, look at what happens with flux melting, because igneous petrologists were sampling the volcanoes there and have come to the conclusion that the dacites that were erupted are produced by fluid present melting rather than by programmed heating. So very interesting to tackle the problem of flux melting from the cooling andesite water into the host. And what I mean basically is how I envision this is you can have the andesite here cooling, so the melting it is becoming enriched in water and it's fluxing the water into the host. So once it hits the host, what we have is dissolution of the matrix and the lowering of the melting temperature that leads and somehow it dilutes the concentration of water in the pores. But as you have continued water influx, matrix dissolution continues, and decreasing the melting point and so on in a loop that would lead to the partial melting of the host. So I think it's a good place to sort of analyze the shearing mechanism two-phase with phase transition, and see if we can reproduce the constraints that petrologists have put for this problem. Also, in the same vein, we can think of the andesite as a two-phase system, so crystallizing system that is cooling, and again, see if there's competing effects between closing porosity by solidification and perhaps dynamic pressure effects that could affect the solidification temperature, perhaps open window for channelization and opening for fluxing or enhanced fluxing into the host that could lead into this mechanism of fluid present melting. So this is very interesting in terms of understanding largest eruptions on Earth, how they happen, how is melting occurring, and how is the crossing of scales occurring, and how we go from there to Plutons. And this links to crust formation. This is from this magmatic terrain that we extract these granitic magmas that are going to form the crust and bring the elements that are important to life, like chlorine and phosphorus, potassium, and so forth. So also there's some constraints coming from not only the Andean subsurface system, but also from Ladakh, Himalaya. Richard and Weinberg are suggesting that some fluid present melting is occurring there, where the dikes and the shear bands are in place, as I show you. Also, and very interestingly, the Taupo case, like you can, apparently geochronology suggests that you can potentially melt the whole proterolism very fast. So heat and heat conduction is definitely not going to do it in those time scales. So what are the mechanisms controlling fast melting there? And of course, I also would like to put together perhaps a linear model for the lower and mid system, linking these ideas of andesite, basalt differentiation into andesite, and then localizing strain and enhancing flow through dikes into the shallower system, and compared to what we have in terms of volumes, and that comes from tomography and so on. And, yeah, I think that's all I want to say. So, thank you.
Thank you. Questions for Mikel?
So what are some properties that seem to correlate with, say, bacillus size or dike width? I mean, is there a correlation with magma flux? Is there a correlation with the contrast in density between the magma and the surrounding rock in which it's intruding? What are
Yeah, influx. Well, I haven't worked on that part, but what I gathered from Bedford and Company, yeah, it's pretty much the rate of thermal flux and mass flux through the dikes. And
so do bigger intrusions occur with greater
right,
magma
but
fluxes?
I don't know, because it's unclear to me how the space making problem to me is still open. Some say that you can have viscoelasticity there working in making space, but I'm still unclear about how the host accommodates all at high flux rate all this deformation without damage. And as far as I know, and link this of course to perhaps seismicity if you do it fast enough, as in the case of Taupo. So to me it's an open problem how this occurs in real rock, and taking into account realistic damage rock mechanics. But yeah, higher flux rate and higher volumes, but again where I get lost is in the mechanisms to accommodate the formation fast enough to allow 1,000 cubic kilometers in place there in moderate years.
What observations might suggest Rayleigh Taylor instability as a
Oh,
focus in
Yeah, no, as far as I know, it's just based on physics. This was for the lower crust, some Russians did modeling about 10 years ago in the example I showed. And I think it's very hard to constrain from empirical evidence, right? It's more like, well, physics would allow it if you have enough thermal flux and you have this specific viscous rheology, behavior on realistic rocks and so on. It could transport mass and thermal energy through relic Taylor, but I would say it's just a good hypothesis based on physics, but very controversial. Not that much in the lower crust if, again, you have a lot of it. But for me, then upper crust is rather controversial because of it demands viscous flow of the heaviest. Again, real rocks don't flow like viscous fluids unless you make very vast approximations in the long term.
Any further questions? In which case, can we just thank Mikel again? Thank you.